Okay, so let's continue on. So computer consistent loads for the two element. We have a linear varying load over an edge. And now we want to first, what I want to do is just confirm for you. I've already asked you to do this, but on your own. But now I'm going to just do it formally so that we just make sure everybody is on the same page. What I've put down here is the shape functions from N1 to 8 for the Q8 element. You can go to page 305 and look at that Q8 shape functions, N1 to 8. They then get assembled into this N matrix, which is essentially a 2 by 16 matrix, where every so at the first position, third, fifth, all of these odd positions, when I have it in shape function N1, N2, N3, N4 up until N8, this represents sort of the X stuff that happens in the X field. That's really what this boils down to. And if I look at this one, which is at all the even numbers, this is for helping to interpolate the Y field, things that are in the Y direction. That is the nature of how we decided to assemble things. Okay. So essentially, that is just the way the two vector fields, the interpolation of the displacement field in the X direction and the displacement in the Y direction is split in the finite element method for the two-dimensional case. But what is important is when we are looking at now this element here, we know now that there's a linear variation of the stress. There's a maximum stress component there. It goes down to 0. If I only model it with two elements to the thickness like this, I would like to apply maximum stress here, and then it must go down to 0 there. I want to know for this sort of this loading that I have here, what, and this side the loading is sort of this kind of distribution that we have. How would that consistent nodal loads look? Okay, so that's where we're going to. But what I first want to show you is that if I want to be on this edge, I need to evaluate the locally. There's a psi coordinate system that's in the middle, and the eta coordinate system that's at in the vertical direction. And so I need to evaluate this matrix of shape functions at psi equals to +1. Then I'm on this edge. So if I evaluate that N matrix at psi equals to +1, I'm on this edge of this element. And then I can see what other variables that still vary, and they should only be a function of the eta variables, because I've substituted all the psi's for 1. Then it will only be a function of eta that I can have. Sort of a description for what's going on. Okay, so that is important to understand. So let's do that, and if we do that, where I just say this is the shape function matrix, and I substitute psi equals to 1 in here, I then get out for, if I want to interpolate in the X direction, these values out. If I want to interpolate in the Y direction, I get these values out. But for now, we're going to be interpolating in the X direction, the loadings. But this is essentially what we have. We have this value, this shape function, and this shape function. That's that's still a field variable. And you can go and compare these values against your values for your 1D bar element shape functions, and I'm going to show you. I want you to see they're exactly the same. The only difference is now it's not at psi, but now it's in eta, because we've substituted for psi equals to 1. But now we see in linear, we see these shape functions are exactly the same as the 1D bar element shape functions. They just express in terms of eta. That's all. That's the only thing that's different. But for the rest, everything is hunky-dory. Everything is exactly the same. Is that clear? This is an important point, because that means sort of if I were to have sort of a stress that I'm integrating over that edge, so that's going to be an area integral over that edge. These are the shape functions that are going to be playing a role. So I'm going to see, this is why I can make the statement, if it were to be uniform, it would have the same split as a uniform body force over a 1D bar element. That's the nature of it. But now what we can do is to say, these are the shape functions that express what's going on over this edge. Okay? And we can see for ourselves that this first one that we encounter, so this is 1, 2, 3, 4, 5, 6. So 1, 2, 3. So 1, 2, 3. So those two are essentially these ones here. So that's in the in this X direction. This is the 1, 2, and the 3 one. This is these two, and then 4, 5, 6, and then you can count it on, and you see this is the 6 one, which is essentially this mid-side node there. That's it. And so beautifully we can now say, okay, let's go and compute the consistent nodal loads, and by doing that we can really just say, let's just first compute what is this maximum stress. We know what the answer is already. That's 375 MPa. We've already calculated that at the top, but let's calculate it here again. Let's calculate it here again. So this is just calculating the S max, then I can express essentially this linear variation going from max to 0 here. Okay, so you can go and see this is the same calculation what I did at the top. Essentially, I can then go from S max down to 0. So I want to make sure if I evaluate the shape function here, if I evaluate on this edge, eta is -1 here and eta is +1 there because of that local coordinate system. So -1, +1. So if I evaluate at -1, I want to have a 0 stress. If I'm at +1, I want to have a S max stress. So we can go and check if that works out like that. What should the expression look like? I'm putting down the expression here, and you can go and let's quickly go and confirm that is indeed the case. If I put in eta equals to 1, then I get S max divided by 2 times 2. So that's just S max. If I put in eta -1, I get 1 minus 1 is 0, and then I get essentially 0 for S. So this is now my linear varying stress field. Beautiful, very simple expression. And here are my shape functions that I've shown you at the top, that I have to write for you. And I can just quickly, compactly just put them in here, so they can just work on this. Don't have to work with those bigger matrices, just a compact kind of expression. I can put down together my integrand. That's now area integral that we're going to be doing. And the thickness is going to be constant, so that we can pull out. So we're only going to end up with a, so although it's an area integral in the thickness direction, if the thickness is constant, I only have to do an integral in this direction, because then the thickness is just the constant thickness that I multiply by. So that's why I have this integral with the thickness in here, and L over 2 integrand. Okay, so that's really what we have. L over 2 is the length of that element. So that's the element length is h over 2, and L is the element length delta x, or the length of the element divided by the 2 for the length in the local coordinate system. So there's my integrand. I can go and integrate from shape function -1 to 1, and then I can see my consistent no loads is this 0, 125, 250. Okay, that's what we get out. I can show you a way to verify that this is indeed what we expect to see out. If we go back one up to the previous problem that we did. Remember this previous problem that we did? We did the inconsistent load learning, and we can go and check what is the reactions on this side. And I can look at the reactions and see if they sort of correspond to these values. I would expect them to be close. Because remember what I showed you last time, if you want to do the consistent loading, a cheap way to do it is look at the apply a loading that's sort of statically equivalent on the far away edge, and then on the other edge where there's where I model it with rollers and stuff, I should be able to recover the consistent load reactions on this side. And I just want to show you. So essentially what you get out here is the reaction forces. And I'm going to show you what the reaction forces are if I plot them here. The reaction forces are indeed, and this is now, if I go open this input file, you can see for yourself what it is. It's element 1, 10, 15. So it's 1, 10, 15 for the first 3 reaction forces that we'll get out. So that's going to be 1, 10, 15. So let's look at the reaction forces there. And the reaction forces there is minus 125, okay, 0, minus 250. So minus 125, 0, minus 250. And at the top, it's essentially 0, 250, 125. So that's at the top, it's 0, 250, 125. And we can go and check that indeed 0, 125, 250. And 250 here is the mid side because of the numbering that I used here. So 0, 125 for the outmost one, for N2, that is the outmost one, and N3 is the mid side, that's 250. See that that's an easy way to check that things are hunky-dory. So that's all makes sense. And now let's quickly run this, where we apply now this consistent load over each of the elements. So the one element is going to be applied in a way that has it that has a consistent load here, and the other one, so here it's going to be in the negative direction pushing, here it's going to be in tension, so it can be positive. And I can quickly show you by opening up this input file, QH pull 2, you can see at the bottom essentially the bottom I'm pulling, and at the top I'm pushing. So that's really what we have. And those are the loadings that I'm applying. And now we can see, now that we model it with those consistent loads, when we run this, boom, let's make sure everything runs hunky-dory. If there's anything that's not running, let's fix it quickly. Oops, it's going to complain about that, it's going to complain about that. Make sure that is fine. Okay. And what I'm showing here is the following. This magnification factor of 10, I think the other one we did 50, so we can also do it 50. just to have a better idea of how it zooms. You can see here nicely. It looks a lot more like a straight edge there. But let's look at the stresses. They are telling the story. Look at that stress field. 375, can you see spot on? Von Mises 375 max, because the other ones are all 0, from 0 to 375. Beautiful. If I look at sigma xx, minus 375 to plus 375. Look at that beautiful peer bending stress, sigma xx, because we did our homework. We did the effort. Look at sigma yy, 0. That's numerically 0 that we're recovering. Look at the sigma xy, essentially numerically 0. As expected, here's the reaction forces. And now we need to, we can now go and say, let's confirm that this is indeed in nodal equilibrium. You see the reaction forces here are very similar to the reaction forces we had for the inconsistent one. Here they were just approximately those values, because of, if we go the further we go, if we had a longer structure, further away from that, where we applied it, it would be even more accurate. But look how beautifully this is recovered. This is now numerically beautifully recovered. In terms of what we would expect to see for the consistent nodal loads. You can see those values are indeed the ones that we computed. So it's always the two ways to compute consistent nodal loads. The JEPO way and the mathematical way, but be comfortable doing the mathematical way. The JEPO way is not always available. So that's all that we could do, is we can now check that this is indeed in equilibrium. Because if I take 125, I multiply it by a distance of 4 plus 250 multiplied by a distance of 2, and I do twice. Not 4. 125 to the center line. If I take 125 multiplied by 2 millimeters, that's to the center. 250 multiplied by 1, that's to the center. And I do twice, I get essentially 1,000 Newton millimeters. That's really what I would recover, and I want to show you that. So 125 newtons multiplied by 2 millimeters. That's now, because the reaction force here is 125, and I'm multiplying with this distance, that arm is 2 millimeters, and then this is 250 and 1 millimeter. So that's what I'm going to do now. 1 plus 250 times 1 millimeter, and that's going to be only half of the story. That's the bottom, and the top one is going to add it the same. It's the same direction. It's going to be twice that. There's 1,000 Newton millimeter, or 1 Newton meter. You can see nodal equilibrium in terms of newtons is sorted out. Nodal equilibrium in terms of the consistent nodal loads is sorted out, because this is cancelling. These reaction forces are cancelling the consistent loads that we applied. So this makes sure that sum of moments, sum of forces in x and y is all in equilibrium. Beautiful. Okay, and now we can go and compare the solutions between the two. I want you to take time now. I'm going to stop the video, compare the solutions that you saw. Look how beautiful the solution is. As expected, a nice pure solution. We can also trust the answer close to where we did the modeling. We can even ask questions and trust these values. Go back to your previous one and ask yourself critically, would you trust these values for your calculations, or if what you want to use, you're going to be essentially get up to a von Mises of almost 600, where it's supposed to be a von Mises of 375. That's large errors that we are making, very large errors. Please be cognizant. If you want to be modeling stress resultants, if you want to do the JEPO, make sure St. Bernard's principle is at play. If you want to model it properly, or if it's not at play, you have to model it properly if you want to trust the values. You can easily model it such a way that you can't trust it. So hopefully this is clear and giving you a good idea of what modeling stress resultants is all about.